Okay, the next talk will be about low-rank matrix estimation. Leah will give the talk.
Okay, thank you. Hello everyone. I will present this work on, with Marc Lelarge on low-rank matrix estimation. And so we are going to consider this very simple model where we observe a matrix, an n times n matrix Y, which is made of some signal plus some additive noise. And here we will be in the rank 1 setting, so where our signal is of the form x times x transpose, where x is an n-dimensional vector with IID entries according to some prior distribution, and where our noise will be standard IID Gaussian and symmetric. And we had here an extra parameter, lambda, which is actually the signal-to-noise ratio for this problem. And last, the scaling 1 over root n is just the good scaling to look at this problem. And so we will be in the setting where the statistician knows the prior distribution of the entries of the signal, P0, but also knows the signal intensity. Okay? And so he observes the matrix Y and wants to recover the signal X. Okay. And so for this problem, maybe one of the first estimators that you can think about is the spectral estimator. Let's take x hat to be the eigenvector associated with the largest eigenvalue of the matrix that we observe. And this estimator has already been well studied. And there is an interesting phenomena happening, that is a phase transition for this estimator. So when the signal is is below 1, when lambda is below 1, then this estimator achieves only a trivial correlation with the true signal. However, when the signal starts to be high, then the correlation becomes strictly positive, and so we can estimate x well. Okay, so now there is some questions that we can ask. The first one is that we see that this spectral method fails when lambda is below 1, but maybe there is other estimators that can recover the signal. So can we say something about the x in this regime? And when the spectral method works, is it possible to do better? So in the regime when lambda is bigger than 1, and maybe the question that we will try to answer in this talk, what is, in both regimes, the best achievable estimation by any estimator? So that is what we want to study. And what do I mean by best achievable estimation? I mean MMSE, so minimal mean square error, which is just the minimal over all possible estimator of the mean square error. And by considering trivial estimator, you can see that it's upper bounded by this dummy MMSE of dummy estimator. And so another quantity that will be of interest will be the information theoretic threshold. That is the critical value of the signal, lambda, above which you can do in the limit strictly better than a stupid estimator, and below which you cannot do strictly better. So you have only trivial performance. So these two quantities are our quantity of interest. And I will shortly go over some related work. There is a series of work about some algorithm called approximate message passing. And it turns out that this algorithm is optimal for this given problem for a large class of priors and of value of the signal. And so in this regime, if you study this AMP algorithm, then you are able to compute the MMSE. However, when the signal is sometimes too sparse, then AMP is not optimal anymore, and you need additional technique to make it work. So that's this work. And last, I have to mention other proof techniques that use a nice contiguity argument to obtain bounds of the information theoretic threshold. So that's it. And I go now to our main result. That is the exact formula for the limit of this minimal mean square error. And this formula tells you that the MMSC converge to the dummy MMSC minus this quantity. And this quantity is simply the maximizer of this scalar function, a simple scalar function that depends on P0 and of lambda. And so you see this function is quite simple to study or to plot. And so once the minimizer of this function is strictly positive, then you can see that you can do better than chance for estimation. But whereas when it's 0, then MMSC goes to dummy MMSC. Okay, so we have the formula for this MMSC, and I will now show you some plots of the results. And I will here consider a particular prior, that is this kind of prior, and that is simply the only probability distribution over 2 points that is centered with unit variance. So it is of these forms. And why is this prior distribution interesting? Because you can show actually that the problem of community detection is on random graphs can be related to the corresponding matrix estimation with this kind of prior on your signal. So if you want to study asymmetric community detection, then that is an interesting problem to look at. And what are the curves? Here it is. I plot the MMSC and the MSC of PCA. And what we've seen before is that PCA only perform well when lambda is larger than 1. So, but below 1, it's only a trivial performance. And it starts to decay after lambda equal 1. But what our formula gave us is the blue curve, the curve of the MMSC, which tells you that below, say, 0.5, you cannot do better than chance. But after this point, then it is theoretically possible to do better than chance. And so the MMSC decay rapidly. However, you see that the spectral method cannot achieve this optimal performance in this region. And even AMP starts to be optimal only after lambda equal 1. So here we have like 3 phases. The first one is the impossible phase, where you cannot do better than chance. The hard phase, where it would be possible to recover the signal, but we don't know any algorithm to do this. And the easy phase, where we have various algorithms to recover the signal. So last, we can represent this 3 regions on a phase diagram with lambda here and the asymmetry parameter here. And you can see here the 3 phases, easy, hard, impossible. And something interesting happened, that is when the community are symmetric, then we are at 0.5. There is no hard phase, but as soon you are symmetric enough, then an hard phase appears here. And so that's an interesting phenomenon. So I'm done with it. Thank you very much.
Questions?
Yes.
I'm not sure to understand how specific is what you showed at the last talk. Is this value 0.2 something? Is it like for any system, or are you choosing a specific setting?
For every what?
I mean, every system, every setting?
No, that's not every setting. That's this particular prior. And so that corresponds to asymmetric community detection.
The prior you showed with the 2 values?
Yes, that's for this kind of P0. Okay. Yes.
Just, isn't this problem sparse PCA or am I?
Yes, if you take you can take other kind of prior. Maybe you can take a Bernoulli prior. Maybe you are 0 with probability P and 1 with probability 1 minus P. And you can also plot the same things, and you will see that when the signal is sparse enough, then you will observe such a regime here, hard phase. You can take any prior you want for this problem.
Okay, let's thank the speaker again.